So today we have the presence of Professor Jan Kosny, and he has I'm going to tell a little bit about him, in case you don't know him, because he's a worldwide known celebrity, especially in the area of PCM application in buildings, but not necessarily restricted to that area. We have been learning a lot from his visit to the University of Aveiro, thanks to a grant from Fulbright, as a Fulbright specialist, to which I'm very grateful. And also I'm very grateful because he accepted this invitation and he has been with us for a few days. He'll be talking about the advantages and challenges in the usage of inorganic, salt-based PCMs in buildings. And I would like just to give you a short note, curricular note on Professor Kosny. Is a research professor at the University of Massachusetts Lowell and the former director of the Building Enclosures and Material Program at Fraunhofer Center for Sustainable Energy Systems in Boston, Massachusetts, and also executive director of the North American PCM Manufacturers Association. Before moving to Boston in 2010, Dr. Kosny had worked as a senior scientist for almost 20 years at Oak Ridge National Laboratory at Oak Ridge, Tennessee, and he has 40 years of experience in building physics and research institutes. He has authored over 150 publications, 200 presentations, and several patents in this area. He received the Research and Development 100 Award for the development of flame-resistant PCM-enhanced thermal insulation. Thank you very much for your presence, and please, Professor Kosny.
Hello, thank you very much for the invitation, and it's my great pleasure to be here and present to University of Aveiro and other universities on the transmission line. As you can see on the screen, the topic will be associated with PCMs, inorganic PCMs, and I will try to share with you some experience, knowledge from my work in the United States and several other projects around the world. So here's outline of the presentation, what I'll be talking about. We will start from the general background about energy situation in the United States, because most of my research is located in the United States, and a lot of assumptions can be sometimes a little bit different from what you guys would consider here in Portugal. That's why it's good to understand what is potentially difference between Portugal and United States in a so-called energy usage landscape. We'll talk about a little bit about history about conventional, sensible, and latent heat thermal storage applications, advantages of thermal inertia management in buildings from the perspective of different management of peak loads and dynamic loads in buildings. Then we'll talk about specific advantages of inorganic PCMs, considering that organic PCMs are a major product right now on the PCM market in different applications. It's good to realize how inorganic PCMs are different. Then I would like to share with you a little bit on my current work on inorganic PCMs. Also, one of the topic will be specifically dedicated to calcium chloride hexahydrate, which is one of the lowest cost PCMs and placed in very convenient temperature band when we look for the temperature activity. Then I will just mention one thing which is very important. We cannot use in buildings a PCM. It has to be very specific, a very specifically selected PCM of specific thermal characteristics. Without this, we may be in a situation like happened many times during last 2 decades around the world. thousands of projects when architects came to manufacturers of PCM and they asked, I need a PCM for my building application. And then they put that PCM without consideration of any thermal characteristics required for that specific place. That happened for decades, many times, and that's why PCM industry is right now suffering so much when it comes to building applications. And actually, I'll be ready for a couple questions from you guys, and if somebody is online, we can also entertain questions. So let's start with the first thing. Energy situation in the United States. I don't want you to remember numbers because I'm using both units, imperial units and SI units, and sometimes it may be confusing, so I don't want you to just convert, even if I'm giving conversion most important numbers, just don't try to convert numbers, just to try to remember proportions. And in North America, I'm talking US and Canada, the buildings represent, in general, 40% plus building-related construction work is about 6-7%. So we are very close with buildings. We are very close to the 50% or to half of the actually energy consumption in the whole country is associated with buildings. We have industry representing 24% transportation, lightweight transportation and heavy-duty transportation. That means it's commercial transportation. They together represent about, I think that's 27% or something. So that's the general portfolio in the United States. Now, we have two sectors within buildings, residential building sector and commercial building sector. Residential building sector is, I think that about 55% or close to 60%. Commercial building sector is smaller. If you look right now for the loads, actually for types of the energy consumption in residential sector, you will see that actually major component is, we have several components, but major component is space heating. Then we have water heating, space cooling, and several other small things. And there are others. In some buildings, especially in urban areas, that others mean, we call this in-plugs. What then means? Anything which is sitting on the table, hanging on the wall, like TV. They are just very quiet things, but sometimes there are locations when they consume 50% of energy for the building. So they are just like killers for energy conservation. And you can just spend your life trying to minimize energy conservation in buildings, reduce something 2%, 3%, 5%. Immediately, you have like people living in a house with a big aquarium, which takes tons of energy to run, or some other stuff. And you have completely no impact, no codes. There are very strict codes, like energy building codes. So you have strict codes how to build building. If you need to put 2 centimeters or 5 centimeters of insulation, you have to do this. Otherwise, building will be not certified for usage. We are fighting for small percentages of energy usage when we have completely no ability to impact the huge packed. Remember, sometimes that gray area, it's really gray area. Sometimes it's just over 50% in some types of buildings. So this is a residential building. Also, I circle. Please mark on those circle things. They are dynamic loads. What does it mean? That those dynamic loads are going up and down. Depends on time of the day. PCMs, and we have to connect. Thermal mass and PCMs, thermal storage, are working with those dynamic loads. So they are completely useless. If we'll have everything steady state, thermal mass will not have much usage. Thermal mass have a sense when we have dynamic loads, external loads and internal loads. Please notice that in residential building dynamic loads, it's my estimate, it's not official, it's about 79% of the whole load in US sector. If we go to commercial buildings, picture looks very much similar. We have space heating being the largest one, of course, not in Portugal. That's why I said it's a different situation. We talk about northern countries. And if we go together, we can see that actually dynamic loads are even higher, 87%. So we have those loads which can be regulated in many ways by thermal mass. Here's another chart showing how loads, you can look for that bottom chart, you can see how actually energy consumption, different type of loads, change between 2003 and 2012. So this is that chart. You can see that actually some of them grew up, some of them decreased. So if we can see, for example, space heating significantly was reduced, lighting significantly was reduced, because simply we came to a new generation of lighting. But some of them, like cooking, cooling, computing power, refrigeration, increased. So we can see that actually everything is going up and down. The biggest loads are going down. Then the top chart is showing the distribution of different sources of energy. The yellow part represents energy. And we can see that actually it has been growing up, growing slowly, but right now we'll have very rapid increase because all countries in Europe, in North America are looking for electrification. So we will be trying to reduce, for example, gas consumption, coal consumption, other sources of energy through the electrification. Here is energy consumption by source in the United States, and we can see that actually natural gas, petroleum are representing very significant parts of that energy. Renewable energy is about 10%. It's I think that 12% right now. And I expanded that renewable energy into different components. And you can see that actually hydropower is a very significant one component. And we have on very top, we have geothermal, solar, and wind, 3 components. Those 3 components are about 2.7 quart of energy. So this is about 2.7%. Whole American economy, energy economy is about 100 quats. So that's about below 3%. But you have to remember, if we go to previous chart, this is 4 times whole renewable energy resources right now are 4 times lower than the dynamic part of the energy consumption in buildings. That's the major dynamic part. So this is very important to remember, how big potential dynamic components in buildings are. Let's talk about a little bit of history about sensible and latent heat usage in thermal storage in buildings, and why we are using that heat storage. So historically, in the past, it was to provide minimum comfort. We try to live in just minimum level of acceptable thermal conditions. Then, in time when BASF introduced micronal, people started to talk about PCMs. In time when in the US people started to do passive solar heating and cooling, we start to talk about energy savings. So that was the second target for the application. Right now, the target is completely different. We are talking about dynamic. Of course, each one, comfort, energy savings are still important, but on top of everything right now, we have dynamic load management and grid integration. And I mentioned this several times in conversation here with different groups of faculty, that this is not only energy-related topic. This is not only sustainability-related topic, but for most countries right now around the world, it is national security-related topic. We have to realize national security-related topic. Why? There have been several research pieces around the world looking for climate changes. And we know very well that climate is changing in the way that temperature will increase, and we'll have average temperature everywhere increase. But this is not whole true. The whole true is also that dynamic of the climate significantly change. So all those events, which sometimes we have 1, 2 times, 3 times a year, will become much more often, like hurricanes, floods, like big snowstorms. This will become just almost not on daily basis, but will be much more often. More interesting is that during those extreme events, peak energy demands will be significantly higher. That means that our peak load and heating or peak loads for cooling will be not, let's assume, 100% like we have today. They will be up to 400% higher than what we observe right now. It is very important to remember because buildings and whole energy consumption system like power grid and energy production are not designed for average loads. That whole system is designed for peak loads. So it is anticipation that actually in Northern Europe, we may have situation that probability of energy breaks. That means that time when a power system will be not able to supply power for the users will be, that probability will be 28% higher than what we have right now. That's what this prediction for Northern Europe. It's good to remember because there's limit how, and we can see how flexible energy system is right now in current war situation in Europe. And actually we will see during the coming winter what flexibility of North European or European countries have in power supply. We can look from the political perspective of war right now on this, but we can also look from the perspective of what future climate change will bring. And this can tell us how big flexibility we may have in reacting to those very high loads. So this is very, very important fact to remember, and I purposely stopped a little bit on this topic because not everybody is thinking that way. Just we will have significantly higher peak loads on buildings. And this comes to everything. This comes to the energy, this comes to water supply, this comes to almost every part of our life. For example, population growth in big cities. So, okay, now let's take back.
That's what I found.
Sorry. Let's go back far away back to history of human beings. We grew up as human beings in caves, and that's why our thermal reaction system has been well developed with one condition. We would like to have uniform temperature film around us. This is something where we feel okay. When we have some places with significantly different temperature, we feel this immediately. If we have some locations with significantly different air velocity around us, we feel this immediately and we react on this. Our system is very much sensitive for those changes. So it's good to remember that actually human beings would like to use specific conditions. And actually as much we have, every country has building standards. And I've been involved in creation building standards in many different countries around the world. This is something to remember. Just those standards not necessarily represent human beings. They represent energy conservation. They represent construction requirements. They represent safety. But when it comes to the question, okay, how human beings will live in those buildings, there is not necessarily always, that question is not necessarily always answered. And actually, there is a try to answer, for example, for average temperature in different rooms, or humidity level, or CO2 emission limits. So there are some tries. Okay, so let's go to talk about thermal mass. Couple examples of completely different technologies in different parts, climatic parts of the world, when people have been using thermal mass. Historically, if we look on the top, we see just ancient times people used a lot of stone in North America and also in Asiatic and Africa. People have been used a lot of clay structures. And northern countries, people use solid wood, which work at the same time as insulation and also thermal mass. I just put the slide which is telling him briefly when we can find thermal mass in current buildings, what can work as thermal mass, and we can see there could be something which is involved in structure or something we can add to the structure. Like, for example, concrete slabs or even containers with the water or some kind of thermal fluids. Important just to remember the scale, how significant capabilities thermal mass in buildings. I just took the Empire State Building, and I just did calculations considering how much mass is involved, structural mass is involved in buildings. And I don't want you to remember numbers, just one number. If we assume that all calculations are made for 5 degrees delta T, Empire State Building is equivalent to 26,400 Tesla Powerwall batteries. This is how, and ask yourself a question right now, how many buildings we have like this in the United States? How many buildings like this we have in Europe? This is the huge potential. And ask yourself, is it any company around the world which can produce that amount of batteries for store energy? No way. We don't have even lithium, enough lithium around the world. So it's good to realize how big potential is in good engineering and good management of thermal mass in buildings. Of course, everybody will tell that actually that energy stored in batteries is much easier accessible. Agree? This is not that easy accessible, but we are engineers, yes? And our role is supposed to be in making this as easy manageable and easy accessible. So remember, for delta T, 5 degrees, we have about 26,000, one single building. If we assume delta T 5 degrees, like I said, a lot of my colleagues around the world are considering for evaluation of thermal mass, we'll have 52,000 Tesla batteries. Each Tesla wall battery is a 7 kilowatt hour. This is capacity. Okay, now, not every structure is heavy. Call that structure thermally massive. We can add thermal latent heat, like phase change materials. Good example of phase change materials are 2 glasses of some, let's say, Coca-Cola. And you imagine that you are walking through the street in the middle of August, Porto or Aveiro. It's like crazy hot. And for half an hour, you walk with those 2 glasses. After half an hour, you try to drink from left hand, which is without ice, and right hand with ice. Left hand is not very pleasant to drink. The right hand is a completely different story. We like it. So let's imagine that we have 2 houses. And we have one house roof with completely typical conventional insulation. The second house has a roof with added phase change material. I'm not telling how. And let's assume that that thermal phase change process in that house on the right is about 30 degrees. So what's happening in that house on the left side, in 10 o'clock early morning in the attic and under the roof, that means that the thermal load going to the house, we're starting to have high temperature. And that temperature can be 40 degrees, can be 50 degrees, can be 55 degrees, even 60 degrees. So this is the scale of the load, what we have going to the house. On that house depends on how much of thermal mass we have that add in phase change materials. We can have situation that at 10 o'clock, we still don't feel anything. 11 o'clock, we still don't have anything. 12 o'clock, we still don't have anything. Temperature is just as used to be. 30 degrees, our phase change temperature. So we can, for me, normal practice is that system designs like this, they can easily provide 4 hours delay in time. So you can see how big, powerful technology it is, and you could see how important the technology could be for Portugal. You guys have wonderful climate here, with loads going up and down, and with temperatures going up and down, and also with loads going not extremely high or extremely low. So you can use this almost for the entire year, especially, I would say, eliminating heating loads during the winter. Okay, so this is what we talk about PCMs. There are several types of PCM. Water ice phase change process is the easiest and best recognized by everybody, but we have 3 groups of the PCMs. Inorganic PCMs, like salt hydrates. Organic PCMs, waxes and paraffins are a good example, but there are many, many different organic PCMs. And eutectic, there are different mixtures of the different types of the phase change materials. how PCM works. And if you can see on the bottom line, that solid line, we have material going through the heating. Temperature is increasing, material is still holding the same temperature. Energy is just, material is giving out his cold energy. Then, at some point, material doesn't have any storage, so temperature is increasing. We call that point when the temperature is starting to increase as a melting point. Then we can chill down material. And most of the materials, especially organic, they have very close freezing point with the melting point. Inorganic materials, in inorganic material situation is a little bit different. We need to have much lower temperature for freezing material or solidification material than during the melting process. We call this subcooling. There are many different reasons for this, and I will tell a little bit, but please remember those 3 different errors, which this is the first one, melting temperature range, which is different from cooling, freezing temperature range. And if you overlap those 2 ranges, it is temperature, functional temperature range for PCM, specific thing. And this is what's most important we need to know about. If we know PCM, we need to know how high we have to go, looking for climate conditions or temperature in specific location, and what should be minimum temperature when we can achieve, just to make sure our PCM will freeze. Okay, first PCM house. Have you noticed? People have been knowing PCM houses around the world for centuries. First successful application, not only PCM, but also PCM enhanced thermal insulation. Beautiful, the best solution for housing in northern climate. This is really first time when people use PCM in architecture. And Maria Telkes in Massachusetts, in Dover, Massachusetts, in 1940s, she built house. Actually, before she built it, she was chemist. And she actually, before she started building that house, she checked climate data from Massachusetts. And she checked that during the last 60 years, the longest period of the time when there was no sun, it was 9 days. So she designed, you could see this looks like a passive solar application house. This is a practically Trombe wall, which has been developed like 20 years, 30 years later by Felix Trombe and Michel. That house worked like the glazing. There were drums behind the glazing containing phase change material, inorganic salt material. She was able to keep that material working for 2.5 winters. And actually, that material was providing 100% of energy for heating for that building. There was no other heating system. So you see, it could be, phase change material could be successfully applied. Of course, she didn't know at the time that salt hydrates, and it was calcium chloride hexahydrate, which I'll be talking later about, disintegrates. So she was able, before whole material disintegrated, and actually major problem was corrosion of those drums. So before everything just started falling apart, she was able to have that system working for 2.5 winters. I gave a couple examples how and where PCM can be applied. You could see the different PCM as a part of as a gypsum board. You have actually, I saw my colleagues from Aveiro University, you guys have been working with bio-PCM, so there's another example. There are another example of different applications. Several of them actually I developed. So actually you can see that fiberglass application with PCM. It's one of my patents. You can see PCM application in blinds as well. So here is example of the commercial applications of PCMs in many different places. I had a question about floor application for solar heating, for radiant heating on floors. There is one of the examples. A lot of examples of the application on the roof. And actually, this is one of my experiments from the past. This is very interesting. Actually edit the floor in computer rooms. So this is commercial systems. You have very high convection underneath that floor and thermal storage in the floor material. I gave a couple examples of the systems using PCM technologies. So there are successful demonstrations. You can see first, I think 1, 2, 3, 4, 5, 6. There are around the world application, Germany, UK. This is the BSF building in Ludwigshafen. This building is metal structure in France. This is German building, one of the first best known German buildings in Berlin. This is, I think, the University of Newcastle, lighthouse by Kingspan, also in UK. This is a building built in Australia, PCM. All those buildings is BSF Micronaut. And this is the first one. This is one of my buildings, first of my buildings, when we can see application of different microtech PCM. And this is that here in this building there is application of cellulose insulation mixed with PCM. Here is the application in the state of Washington, also PCM provided by Bio PCM, North Carolina PCM. So let's talk about advantages of thermal inertia management in buildings and in power system. So historically, we use thermal mass to stabilize interior space temperature, improve thermal comfort. That's mostly comfort-related application. Now, today, there's different function related with thermal load management, and we're talking about, of course, summer loads, cooling load, and heating loads during the winter time. When you go deeper to those loads management, we see that actually what we try to do, we try to shave the peak of the load, make smaller load peaks, and we try to shift the time of the peak. There are two things, and that's achievable with PCM, not easy achievable with mechanical system. And surprisingly, it's much more attention paid around the world for people trying to manipulate loads with mechanical systems. And also, one in the very important fact is that we can manage that, I would call it, load reshaping or changing the shapes of peak loads with PCMs or thermal mass. It's fact that we start to have a lot of extra dynamic loads in our economy. What are those extra dynamic loads? And I'm not talking right now about building, I'm talking about the whole economy. So what we have. If you remember, buildings represent 40%, yes? 40, 50%. But we on top are adding electric mobility, which are very dynamic loads. We are on top of this, we are putting extra renewables, which are also very dynamic and very difficult to predict sometimes. Wind, for example, or sun. So we are adding a lot of dynamic components. And we are adding also thermal storage, seasonal thermal storage for cities. This is how everything's starting to look like. And actually, we call this in US dark chart. And in most civilized countries, that dark chart looks very much the same. This is energy consumption along the day by building sector. And for residential buildings or commercial buildings, it can be a little bit different, but not necessarily much different in the way. And you can see that it looks like a duck, yes, sitting duck. Now, if you see that light blue line going, this is typical building. We have two peaks, early morning peak, about 7 o'clock, 8 o'clock, little bit of energy consumption coming up. And then we have continuous energy draw by building sector, and then we have huge peak afternoon hours, correct? This is important to remember that actually if we will get to that peak solar part, what we are getting, we have negative energy, yes, going to the grid. So that we have that belly growing. More solar, we have that belly growing. And we are getting to the point that actually we have to start shutting down power plants. You know, you cannot shut power plant because power plants are designed for specific capacity. And if you shut down power plants, it takes sometimes a week or two to make sure that you will be able to put this back in operation. So in that situation, you have to go and make sure that that belly is as small as possible, correct? The second information you need to know is that actually the optimum situation in load distribution will be that flying duct. You see how loads are looking? All that chart is very much flattened. It can be achieved just by superposition of several effects, and one of the effects is energy efficiency. So energy efficiency just reduce all those parts a little bit. The second significant effect will be thermal storage. With thermal, what we can do with thermal storage? With thermal storage, we can, I wrote this out, we can cut that peak down, and with thermal storage, we can easily move it here, correct? So as a result, instead of sitting duct, we can have flying duct. And that flying duct is supposed to be a symbol for the well-organized national, for many countries, national energy policy. Not only buildings, national energy policy. When we try to balance not only buildings, but also renewable energy sources. This is unavoidable. Otherwise, we will get to the situation that country will be not shutting down power plants, but we will be shutting down people having renewable energy sources. This is usually private operated and privately owned. People invest their money. And this is a very unpleasant situation when you make investment and then you are told by your energy distribution company saying that you have to shut down your operation because simply we have too much energy. This happened several times in Chile. I remember Fraunhofer have been involved seriously in development of solar power in Chile, and Chile is one of the leader countries around the world in photovoltaic generation. They were in situations several years ago that country asked companies, take energy during the peak time during the day, and we will pay you for this. So actually cost energy was negative. Can you imagine something like this? They didn't want to shut down power plants, and they didn't want to put photovoltaic investor in inconvenient situation that they will be losing money on solar operation. So this is something which is very important to remember. We need to have very good balance. If that balance is not operational, manageable, the country can actually, especially with coming loads, we imagine there is prediction that now that loads for building peak loads can be a couple 100% higher. And we will need to find the way to react for those loads. It is not easy to add that much of capacity of power production at any country or power transmission. It will have to be a worldwide revolution, building power plants everywhere and building transmission lines. It will never happen. So if we stay where we are right now with current understanding of thermal mass, thermal management, and energy management, energy dynamic management, we will end up in a situation that that part will be eliminated. What does it mean? Solar power will not be able to produce, to show its capability, demonstrate its capability, use its capability. And what does it mean? That we still will depend more and more on the conventional sources of energy. So the only way to move on from the coal, oil, gas to new generation of energy is just to understand those processes and to make those processes manageable. This is like opening the door. This is the just condition. People don't understand. We can build a lot of plants, but still we will have those peak loads. And we are not able to build the peak loads to the level, we are not able to build the power generation and power transmission industry to that point that we'll be able to supply a couple hundred extra percent larger loads, peak loads. Okay, let's go to the thermal mass. How thermal mass works in building, just to make sure that we have tools to operate that whole system. If we have thermal energy daily, this is thermal excitation coming to the building mostly from the sun and temperature swings. That excitation is usually transmitted through the building envelope, through the roof, through the walls. and depends on how much of thermal mass we have in the wall. That whole transmitted line can do a different way. It looks completely different. We call this thermal damping, and we call this thermal lag. That means that that peak, we can see this on internal side of the external wall. It's in different time than this peak, which is on external wall. And we can see that actually there's significant reduction in amplitude. This is example how it can be manageable. And this is one of my experiments. Some of you can recognize PCM used here. This is roof, conventional roof. You can see that line here. This is the temperature underneath the roof. And actually this is heat flux under the roof. And this is the heat flux under the PCM roof, advanced roof. You have conventional roof, the same R value, the same thermal properties. The same roofs can follow standard requirements. Everything is the same except that the other roof has special design, dynamic design. Load has been reduced 92%. Peak load, actually, at this moment is 52, but total load is reduced about 60–70%. Another example. This is something what actually I should show to our colleagues from Saint-Gobain. This is one of the Saint-Gobain systems which this is one system, one of the systems which I designed for Saint-Gobain. And we have three roofs. Conventional roof, roof with special thermal break system with ventilation cavity, and the roof with PCM system. And you can see that actually you can achieve a lot with no PCM design. This is the reduction of the peak. This is the PCM extra part. And actually with PCM you can get this is very important information. Shift in time. I would like you to remember, with envelope, shifting in time for hours is something which should be called achievable. I can achieve also 8 hours. I can even go over 8 hours. But this is something which is achievable. And you can achieve this in walls, you can achieve this in roof. This is another example, and we talk about time delay. It's another shift and temperature reduction. You can see how different is temperature in those roofs. We have, here is about 60 degrees Celsius, and PCM roof has 40 degrees Celsius. So it's about 20 degrees reduction. Imagine in your houses, you live in the 4th floor. On top of you, there is a roof insulation, and it's very unpleasant living this during the some days. I know this because that was my college time. I lived in the dormitory on the 4th floor. Summer was not pleasant time. So you can reduce this time. It is something I'm just appealing to you guys as engineers. You don't have to remember those designs. I would like to make sure that you keep in mind that this is doable. That's all. You will figure out a better way. I'm just giving a couple examples. This is the tricky thing for wall insulation. And then what you can, that system has been designed for Florida. That system has been designed for just concrete masonry wall. So this is just part of the masonry wall here, CMU wall. Nothing different than you guys have here. And then on top of this, we designed two systems. This is typical system using plastic foam insulation. Just people have been using this everywhere. And this is system using phase change material with some kind of different tricky configuration when both those systems have the same R value. So I was adding the same amount of the material to the wall. Cost was just comparable. Nothing, believe me, this is nothing fancy. This is not like a spaceship material. Nothing is fancy. Just everything is just almost everyday usage. Actually, here we use PCM, which has been used by one of the companies for clothing. I didn't have different other sources, and I needed several temperature ranges, so we used that material. And you know what's happened? We measured temperature on the concrete behind the insulation in both cases. This is the temperature of the conventional part of the wall. This is the temperature on the PCM insulation. You can ask yourself how big difference it is, and it is very significant. This is like 70, let's see, 76 to, I think it's 70, 80, 90. So it's about 15 degrees. Again, it's achievable. That part of the advanced thermal insulation is achievable. And again, this is a great, I'm showing this for you guys because you have different climate what I have in Florida. In Florida, temperature is sitting during the summer just very much in one point. You guys have temperature going up and down. Wonderful the climate for using phase change materials and thermal mass. Okay, so let's move on. We did a lot of experiments, but we also did a lot of the calculations. And actually, this is one of the examples of calculations. You can see that actually you can consider, let's assume that this is a solar temperature. You know what solar temperature is. When you add the component coming from the air temperature and solar temperature, and this is, we created that solar temperature that represents external temperature of the wall under the sun. So you may have extreme sun situation, you know, quite big peak during the day, and not so big peak. So we just did 3 scenarios during the day. So it looks like that this is the temperature of the wall during the day. And we have here example of 3 types of the insulation. One insulation, all of them, they have, they are 14 centimeters thick at level of insulation. It's mixed with PCM, considering 30% of microencapsulated PCM. So this is fiber insulation, could be fiberglass, could be cellulose, could be something else. Mixed, or can be foam, mixed with 30% of the PCM. And then that dotted line is representing scenario. This is the largest peak. That orange is just that medium peak, what you saw in previous slide, and this is the small peak. And you could see that actually that we have significant shift in time. That solid line represents the scenario when we use PCM. Dotted line is no PCM, it's just insulation. The other one is with PCM. So you have 2 parts: non-PCM, PCM, non-PCM, PCM, non-PCM, PCM. You understand this chart right now? So there are each scenario on those excitation are represented right now with 2 parts of the configuration. And you can see that actually in each part there is significant shift in time, yes? And there is significant reduction actually. You have the higher excitation, higher temperature increase with the lower thermal effect. Simply you don't have enough PCM. So you will have to add PCM, and you will see this on next chart. But if you have lower thermal excitation, you have more significant effect. So this is for something which is 14 centimeters thick. This one is 30, I believe 30 centimeters thick. So this is roofing insulation. And you could see that actually impact is much more significant. Impact is showing how big it is. For example, here is material without PCM, material with PCM. We have significant reduction of the load and significant time shifting. It is good to remember that actually I have a lot of colleagues who are saying that phase change material has to be associated with highly conductive environment, just to provide just a rapid accumulation of the heat. And that's correct in fast, I call this fast systems. And you need those fast systems, for example, in electronics. In some building applications, you need really fast systems. But in military, in batteries, for example, automobiles. But in buildings, when we are trying to manipulate with the time loads and peak loads times, we need to use slow systems. So that's why people don't understand that actually if you add insulation with thermal mass, you create extremely slow system. And you could see actually how slow system on the next chart. You could see, I put just those peak loads, there's 14 centimeters system and 30 centimeter systems. And I just marked those numbers. This is peak load reduction percentage and peak time delay. And you could see that easily you can go 3 hours, 6 hours, 6.5 hours with that shift of the time. So it is doable. Just the only thing what you need to know, you need to have enough insulation capability and enough PCM, enough thermal storage. That's the two things which are important in that design. And if you have enough, thickness is just the function of how insulated material you have. So you may have super insulation, which will be much thinner. When it comes to the total load reduction, you can see that actually for those systems you can reach even 70%. I would say that would be safer to say 30% load reduction in general. Okay, fire performance cost, environmental benefit, and some other benefits of using inorganic material versus organic material. So first, it is almost impossible to ignite salt hydrates. So that's a good thing to remember. Most of the inorganic materials are very difficult to ignite. The second is price. I put this chart just to let you, there are 3 types of PCMs. Those two, actually 2 types of PCMs, those two are inorganic. This part is organic. And you can see that actually in inorganic, I just created new group, extra group, which is based on lithium-based PCMs. Because, you know, just a lot of people are excited, saying, okay, they are so lithium-based salts are so powerful. Yeah, but they are so costly. This is the most expensive inorganic PCM, which I work on, non-lithium. And this is about $930 per ton cost, total formulation. And imagine that actually we use some additives, which there were 2% of additives on those PCM, which cost about 50%. So without additives, it was about $400 per ton. If we talk about, we have 2 levels of actually we're talking about 400,000 per ton. This is different scale, different universe. Organic PCMs are going over $300, maybe $600 per ton to $4,000 per ton. That's the scale of the cost. So working with inorganic PCM is much better, much easier. They are much less costly. That's the first example. Actually, second advantage after fire. And this is actually, I tried to put this on the scale. So this is those inorganic salt hydrate-based PCMs here. You barely see them. They are organic PCMs. You can see them better. And this is the cost, the whole cost of the lithium-based PCMs. I put 3 formulations on different type of lithium-based PCMs. You see how big scale it is. And actually, I would like to talk a little bit about lithium. The cost per ton for getting lithium different compounds is about $20,000 per ton. And this is not today's price. It was priced from 2 years ago. Also, the price is moving very fast. International assumption is that the cost of the energy stored in lithium-based systems is about $273 per kilowatt hour. And this is cost just accepted internationally based on one of the United Nations programs research. Here we have US DOE price target ceiling for the PCMs. And this target is $15 per kilowatt hour. $15 per kilowatt hour. General, all PCMs, organic, inorganic, versus 270. That's the difference in prices. Now, remember about lithium thing. Takes about 1,900 tons of water to extract the lithium compounds. We're talking about Chile making Chile, converting Chile, Bolivia, and those countries into the deserts, salty deserts. Because when we produce lithium, we also produce tons of the brine, which is drying. So we create just, and actually we take water from whole resources around. Those countries, they already scarce in water. So this is good to remember. And actually, another thing is, when somebody's saying, okay, we can recycle all the batteries to have lithium. Yes, we can do this, and it takes 28 batteries to create one, to recycle. So that's reality, and that's compatibility. And if you remember that Empire State Building, which I showed before, this should show capability, how much we can help environment. Another one, recyclability. It takes about 60 cents or $25 per ton to recycle different type of concrete structures. That's US. Actually, this is California type of the evaluation. Then it takes $24 per ton to recycle building waste. So if you crash building, demolish building, you take this, recycle, it takes about $24 per ton. If we take PCMs, and wood is also about $24 per ton. If we take paraffinic PCMs, actually the only thing is you need to take it, convert it into new products. So there's like almost no cost for recovery, it's just cost for the producing new product. If we take lithium chemicals, it's about $1,000 to $2,000 per ton. This is recycling. And when it comes to the batteries, some countries are talking that they have programs already for recycling batteries. I think that about 5% of batteries worldwide is being recycled right now. And most of the countries are saying openly that actually so far that process is uneconomical. So there is no justification economic to make businesses based on recycling. Everything has to go under some kind of donation, some kind of subsidies. Okay. Current work my team has been doing on inorganic PCMs. And actually, I must say that actually I have a number of the projects where I work from 3 different sources. One is source is Department of Energy, another source is Department of Defense, and another source is industry. When I work not with building industry, I work with the shipping industry. So there are 2 different PCMs, actually 3 different types of PCMs. Most of range of PCMs I'm working with my team is from almost 0 to plus 65 degrees Celsius. So that's the range of temperatures, variety of temperatures. And here is just a couple, I put that slides together just for you, just to realize what are requirements for PCM and how difficult it is to follow some requirements with organic PCMs. First one is price for the cost, $15 per kilowatt hour. It eliminates everything which is of the higher cost or lower density, yes? Then the second, energy density. We talk about 100 kilowatt hours per cubic meter. So it's a volumetric energy density. Then thermal conductivity of material. It's about 1 kilowatt hour per meter Kelvin. This is good to realize that most of inorganic PCMs conductivity is 1.2 to 1.4, 1.5. Organic PCMs are 0.2. So they are 4 or 5 times less conductive. Then important fact is just thermal durability. That means that we need to have number of cycles, freezing, thawing, freezing, thawing, freezing, thawing, without losing of enthalpy. And organic PCMs are much better. They can do million cycles without losing capability. Another thing is subcooling, which is supposed to be at least below 2 degrees. I have my colleagues from industry telling that they will never produce material with subcooling higher than 1 degree. Actually, some people are working here with different inorganic PCMs, and they can say they never saw subcooling so low for inorganic PCMs produced by one of the European manufacturers. I agree. And actually, if you put those numbers together, you will see that actually it's extremely difficult to meet that criteria with organic PCMs. If we add to this flammability requirement, it practically eliminates organic PCMs. And it is interesting that actually that kind of statistic never was seriously considered by major governments in Europe and with major PCM companies for 2 decades. Right now, we are in a situation that PCM is not too much sellable for buildings, and people are asking themselves why. And actually, that chart is actually a very good explanation. They never ended up having products which will be able to meet expectations or requirements. Now, I would like to follow on this difference between organic and inorganic PCMs, and I have on top organic PCMs. So organic PCMs are extremely good when it comes to the durability. They can work and work. They don't have issues with subcooling, but they are flammable. People are saying, okay, they're not flammable, we can put fire retardant. Yes, but if fire retardance is not that easy to do, and actually China is a very good example. If you add fire retardancy during this, the fire situation, you don't have much of the fire, you don't have ignition, but you will have a lot of smoke. And people are not killed in fires. People are not killed in fires by the flame. People are killed in fires by just breathing with the smoke. That's major. So, and another one, thermal conductivity, too low thermal conductivity. So that material is difficult to use really in a serious way in buildings. And actually, this is explanation one. We have so many projects around the world, and so many proud architects who said, okay, I implemented PCM for the first time in Guyana somewhere, and then it happens that actually that material doesn't work. And with inorganic materials, we have significantly higher energy density because of we have material density, like 2, sometimes 4, sometimes 5 times higher. And we have material of higher thermal conductivity. Major problem is that we have difficult to have good durability. And we have subcooling, incongruent melting process, and we have phase separation, which actually, this is challenge for engineers, but I would like to show you in case of next slides that it is achievable. And this is another important fact when it comes to designing of PCMs, because a lot of people don't understand that more we are adding to that PCM, less enthalpy will have at the end result. So I gave example when we have micronal with the enthalpy about 180 joules per gram, then actually this is paraffin. Then we convert this into microcapsulated material, and that conversion reduces enthalpy from 110 to 180 for 110. And then we try to use this material as a part of gypsum board or concrete or something else, and final enthalpy is about 35 per gram. So actually building may not see, if you use this to concrete has enough thermal storage capacity that actually you will not even see that effect of the thermal mass, addition of thermal mass. So this is good to realize, because some people may say, okay, PCM doesn't work in my concrete structure. How much do you add? 5%. Okay. So, just in Polish language, I am Polish, we used to say, don't bring wood to a forest. This is the same thing. You don't need to add thermal mass to stone. Of course, a little bit. You need to add very heavy thermal mass to stone construction. Another very important fact, and this is the explanation one, in many people's designs, PCM didn't work. A PCM, this is another, I started that presentation from talking about a PCM. This is not a PCM. PCM system have to be very well crafted for specific application. And if you look through that building, there are several places with different numbers. And you can see actually exterior wall is number 1, 2 is roofing application, 3 is, what do we have? Water heating or mechanical system application, and for different systems, we have different applications. I listed those applications when we have different temperature ranges for those applications. And this is the first thing designers should know. Okay, I will place my PCM on the roof, so I need to know that roofs and attics require PCM of 35 degrees to 55 degrees. So this is what I should start looking for. Then we need to go to really engineering work. Take computer model, design that whole system. see what is the temperature fluctuation in this specific point, and then get to the point, if you remember my slide with those arrows, temperature band, operational temperature for PCM. And you need to put that operation temperature against that real temperature in that place. This should happen. I bet that maybe happened in less than 10% of projects so far around the world. The other projects were just designed by a PCM strategy. And that's the explanation why so many projects are not working correctly around the world. This is chart specifically dedicated for our approach in my team. And this is coming from my several decades experience working with PCM. We are not working of PCM. We have holistic approach. So this is the PCM part. But we also work on the system part. You will need different PCMs for different systems. So you need to combine that stuff, and it has to be formulation-related chemistry part, durability part. Then you have to go what we have on the bottom, on the left side, cost analysis. Because if we design, and I'm talking to you like part of academia, those people who will be developing those formulations, industry will never adopt the system which will not go through that positive, productive product cost analysis. You may have a wonderful system based on lithium compounds, and you will see that actually industry will say no, no, no. So that's one thing. The second thing is actually you have to design the system which will just carry that PCM. And we have actually several strategies. We can shape stabilize material, like for example, foam mixed with the polymeric material mixed with PCMs. We can have arrays of pouches or containers, or we can have just three-dimensional structures. There's many, many different opportunities, but you have to remember, system has to be designed to carry PCM, not just a PCM. So this is not a solution, and this is first actually recipe for the failure of the system in design in the building. We work on numbers. I said I have several sponsors, and this is on that group of technologies. We have actually 3 PCMs from 4 degrees to 10 degrees, 5 PCM formulations from 10 to 20, 20, 30, and this is the most typical applications. So we have a number of PCMs, and actually that number is growing right now significantly, specifically in this region, because that region is very important for batteries to work, and I have several projects related with batteries. This is the list of the most typical formulations my team is working on. And you have enthalpy, here's and temperature. Some of the formulations were really completed to the point that actually we can pass this to the industry. Some of them are just, just not very, we are not very happy with the results. When it talks to the instrumental and the analysis, test analysis, number one is DSC. Remember, DSC is for very small samples. So, and you have to, if you go to serious DSC analysis, you have to go through the history of the testing PCMs with DSC, because DSC have not been developed for testing PCMs. That methodologies have been developed for analysis of polymers and different biochemicals. So you have to remember about 2 different methods. Step method, DSC testing, that's number one, which actually is the most important, because if you will do industrial way of DSC testing, you will end up with a lot of fake effects. So you may say, okay, my material is not even melting. If you do follow industrial procedures for the DSC testing, it's very important. You have to follow what other people have been doing for decades, trying to learn how to test PCMs. And there's oscillating procedure and step procedure for the testing. I'm just giving examples how important is understanding DSC testing. Second, very easy method, and actually I spoke with my colleagues yesterday, how to build T-history apparatus. It looks like they have everything, so they will be able to put this within a month. It's good for the subcooling analysis, but also good, you can estimate the enthalpy analysis. Example of why it is so important, DSC. I call DSC testing as initial testing. You need to know what you have before you go into more detailed analysis, you need to know at least what you have in hand. So you need to know what is your peak point on the melting, for example, and you need to know what is the spread of the enthalpy curve, because this will help you in designing other experiments. And actually how important it is. Important is actually, in case of inorganic PCMs, it's just, you do DSC for the material, and this is a beautiful chart. You have one peak, but very often situation is that you are looking for one hydrate number, it could be, here is hexahydrate, and what you have here, you have tetrahydrate showing up. And that tetrahydrate is just taking a lot of energy. Your process is here. So you need to have all storage available here in this area. Unfortunately, that storage is here. So that means that your PCM doesn't work too good. And this is very common situation in case of development of formulations. Because just those hydrates are showing activity based on some kind of nucleation sources. And sometimes you are adding either some material which will stabilize PCM, or you have densification material, or some other components. And actually, this will be also nucleation source for that extra hydrate, and screws up the whole thing. Another very important factor, which actually I was told by industry many times. Jan, don't work with those crazy scientists. When I was director of the PCM industry, insulation industry, they told me, because what they do, they work on super pure materials. So they have super distillate ionized water. They have super pure chemicals, which are completely unacceptable because sometimes they're 100 times more expensive than industry grade, commercial grade chemicals. And if you have those materials, you will have completely different chemistry. We are talking about the small pieces, we call them seeds for nucleation, which actually can affect the whole number of different hydrates just showing up, or going into some chemical reactions which are unnecessary. We like them during the process of the making PCM, going from the frozen element to melted element and frozen again. So actually my colleagues from MIT are saying that they're working on crystals. They say, and actually they grow crystals, big crystals, and they say you have to be extremely lucky and extremely knowledgeable to grow crystal. We grow crystals in organic PCMs several times during the day. I mean, we need to be sure that that crystal will grow, not dissolve, nor decompose. So you see the scale, how knowledgeable and experienced you have to be to get to the point that you will be able to design those systems. Another important fact is actually we are using XRD analysis. This is a very important piece of experiment, of the experimental testing equipment what we have been using. Why? Because with XRD, we can see if we have some extra reactions going on. So we can check already, okay, we added that component, that additive to the PCM formulation, and that additive, okay, works well. Here's what we have, but we have several pieces showing up on different places. So this is something we need to know, and for control of the formulation, we need to, for formulation can be called that it is successful, it's going to very rigorous number of testing. And you could see actually there's a lot of chemistry in this whole thing, physical chemistry. Example of the T-history analysis. And we discussed the chart yesterday with my colleagues. So we have several PCMs under the cycling. What do you mean? That we have one formulation, and there's a lot of papers around the world when people are saying, okay, I developed wonderful formulation. That formulation is that much of this, that much of this, that much of this. You mix this, you add something, and this is a beautiful formulation. Enthalpy is 300 joules per gram. You try to reproduce that formulation, and most often you are not even able to reproduce that formulation for one reason. You don't know what kind of chemicals those people are using. So they may have different water, they may have different source of the chemicals. But even if you are reproducing that formulation, you do cycling. And you figure out that actually after this 5th cycle, you don't have any more 300 joules per gram of the enthalpy, you have somewhere 150. And then you go to another 10 cycles, and you have another something like 170. This is going up and down. So it is important to understand those formulations. And also second thing is, it's important to avoid formulations which have enthalpy starting from very high level and then going rapidly down. There are a lot of formulations like this which work for like 30 cycles, and that's all. And then it disintegrate. So you need to go, and usually in the initial work before we go to industry, we go through the 30 or 50 cycles with the analysis. If we go into serious development, we go into 500, 1,000, and 2,000 cycles. And usually, after 50 cycles, we do DSC analysis. After 100, 200, so we periodically take material and do DSC analysis. For what? This is another important fact. The history testing is showing us what is the subcooling effect. Subcooling is something that we have to go with temperature significantly lower than initial temperature. We anticipate there will be freezing temperature to make material go back into solidified form. So this is something which is, just you go through those cycles and you have the whole story of the PCM. The important fact is that after 30 cycles or 50 cycles, we need to have material which is going like crazy, just one line. If you don't this, this is something which shouldn't go to the market. And I will give you just a couple examples of the formulation with calcium chloride hexahydrate, how we work on this and what we try to do. So actually, that material has phase change temperature around 25 to 30 degrees, depends on the formulation. Latent heat between 170 to 190 joule per grams. And we have been working with many different additives just to control subcooling, incongruent meltings, and unstable operation during after the number of cycles. So what we have here, material cost is between $1 to $20 per kilowatt hour, so we are within that $15 target. Paraffins are much higher. Cost, with thermal energy density, we talk about 50 to 120 kilowatt hours per cubic meter, and paraffins have much lower, 40 to 60. So this is just like compare the whole situation. Here's how it looks like, the calcium chloride hexahydrate, and you can see this. This is like a powder. There are several things what you have to learn. We call this cooking PCMs, because this is mostly like cooking. And you have to find the first way. You have to find a way to put together those components and make sure that you will have something which will mix together, will work like one piece. Very often you end with something which is just with phase separation. And there's no way to put them together. You can shake, you can warm up, doesn't work too well. So there are several procedures you have to go through the preparation. Then we do cycling. And you could see actually that we have, with number of cycles, we ended up with cycle number 15 that we have tetrahydrate. Yes, showing up. So, and we don't like that whole thing because this is the main enthalpy area what we would like to have. And that tetrahydrate is making that main enthalpy at this temperature region is small, and then we have another big one. So we actually don't have enough capacity in the region we would like to have. The whole game is starting what to add to that PCM, to that formulation, to make sure everything is stable. And this is, I will not tell all the secrets, but I will show you example that this is achievable. So, for example, we played with different additives. For example, you can see here strontium chloride hexahydrate, which actually operates also with temperature. It also works as a nucleation agent, and actually it helps. We see here that with different amounts of the added strontium hexahydrate, chloride hexahydrate, we have 2%, 3%, 5%. We can have subcooling. This is original without additives, and we have subcooling reduced. But what's interesting, only 2% of the strontium chloride hexahydrate works well. The other parts are just causing, still coming back with subcooling. So you need to find that right cooking recipe, yes? Like cook in the restaurant. Some people are going by smell or taste. Here in designing of PCMs, we have to go through a number of configurations. And there's another one. We need to use a stabilizer. We say that we have 2% of the strontium chloride hexahydrate, and then we use potassium chloride. Again, different percentages. And we are looking through number of the cycles, how they behave. Another one, it is NaCl and sodium chloride. And we see, just it is going that not everything works the same way, and actually not everything is in the process that sometimes we try to add 5%, and 5% is not any better than 2%. So this is the long story about optimization of formulation, and we are not going sometimes 2%, we are going 2.5%, we're trying to optimize formulation very detailedly. And at the end, you have something like this. You have number 25 cycles, and chart looks beautiful, yes? And you have actually supercooling going down. This is exactly what we need. Then we have another formulation with potassium chloride. Also, supercooling is going down. At the beginning, we have a little bit of extra hydrates showing, and then they are disappearing. That's the process. And this is a really long process, so single formula. You need to have good chemical lab and a couple dedicated chemists to work on this, and this is really time consuming. I have 2 PhD students working just almost 24/7. That means that even sometimes during weekends, they sit in the lab and they do that work. And designers, I would like to say a little bit just, it could be a separate class lecture about how to design the PCM systems. Designing about where to locate PCM system is very important. And this is for designers, for modelers. Challenge, you need to be able to put together the computer model of that system, have knowledge of boundary conditions, and put material in different proportions. And actually, you could see that this is actually about the energy savings, but that configuration, you have 0.7% of energy savings versus over 7% in this case. So there's significant difference on the, and I didn't take, just something best performing, lowest performing. I just took just 3 simple configurations to show you that you need to have good knowledge of the system and system characteristics to design the whole system. Conclusions. So actually, I would like go by the pictures more than the text which I show. So there is like sustainable call for using thermal mass and phase change materials right now. For one reason, this is the time we are going through very serious challenges. Challenges with changing climate and challenges coming from extra dynamic loads coming in the whole industry. And in addition, we have additional right now political challenge and war challenge. The second thing is, and also related with environment, we can make sure that actually our systems, those design systems with thermal storage, can be much more energy efficient and much more durable and sustainable than industry promoted application. Mostly I'm talking about lithium-based systems. So we can go much more on environmental side with those applications. And it's good to remember that actually that inorganic PCMs are actually just a challenge for engineers, but also they are beauty because they are non-flammable. They have significant capability for, if they are well designed, thermal storage capability, and also they are not that difficult to recycle. They are just kind of, it's much easier to recycle salt than recycle some either organic chemical or lithium-based components. Finally, those materials can be long-term performing. Just as matter that we will not try to put on the market system which after 50 cycles of the testing, we need to make sure that depends on the application, material needs to have warranty on the significant amount of the good durable performance. And for buildings, I would say this is minimum 10,000 successful cycles. 10,000 up and down, without losing too much of the engine. And the last thing is about design of PCM systems. If you remember, I started that presentation today talking about a PCM. We cannot talk anymore about a PCM. In buildings, in military, I design batteries, I design buildings, I design many different applications, super powerful weapon, and everything is just, it has to be special PCM crafted for that specific application. Also remember, there's not only PCM, this is a system which has to carry then PCM. So that's very important to remember. Those pieces have to come together. If they come together, you will have successful application. Without putting all those components together, forget, you will end up in the whole situation which happened in Europe when PCM have been highly subsidized for 2 decades with zero success, I would say. That's all from me today, and I would be glad to entertain questions if you have.
PCM position, you demonstrated that we have to choose the correct position of the PCM into the constructive solutions, but I would like to know your opinion for the use of different melting points in the same position and in the same constructive solution. It could be a good solution for an annual cycle.
Actually, first, we cannot shoot PCM for the position. Actually, we cannot shoot position for the PCM. You have to know what is the position and then find the PCM which will work in that band of temperature for the specific position. And then, yeah, there are several attempts when people are trying to move on different PCMs of different enthalpies. I tried to. The question is if you can afford this. Because PCM is not the whole, usually in PCM product, the cost of PCM is just 20 to 30%. And I'm not talking overhead about just product in the market. Another 70% of the product is cost of the packaging material. And then on top of this, you have overhead. So if you have total product, cost of PCM is just like 10% or less. So this is not that much. So yeah, if you try to put 3 PCM products on top of each other, this will be cost prohibitive. If you will have single product, when you will have three PCMs working, yeah, this may work.
I have 2 questions. One is a more broader question about the first part of the presentation has to do with the peak loads and the way that we use and manage energy at a bigger scale, and then one on PCMs, more detailed. in relation to the duct graph that you showed, obviously there's two big problems with obviously renewables, and you've shown this with the solar one where we have that dip. We have intermittence of wind and sun, and then we have a storage problem. So we have two problems together. We have intermittence of these renewable energy sources combined with obviously the way that we store, if we have manageable and sizable storage. So in your opinion, this is more of a comment, what do you think that really has to be done, for example, in the States? Reality is different. We can obviously put or bet on different renewable strategies from country to country, depends on our conditions. But how could we manage this? Because this is something that has to do with intermittence and storability. And how can we overcome this, at a national scale?
For me, it's difficult to answer this question from Portugal perspective because you have such a different conditions, specific conditions, which I really don't understand fully. So for me, it's difficult to say. I can say this from American perspective and other countries with similar energy economy like US. It is important to keep that interaction between thermal mass and the rest of the industry in several places. So first, I think that envelopes, building structure is the number one because you can manipulate building loads. And as you can see, actually building loads represent 40% of economies, energy consumption of the. So if you learn how to manipulate with those loads from the building perspective, it's good. With community approach around the world right now, we call about urban communities. Actually, sometimes that part of that approach is coming to community-based energy storage. So you have seasonal thermal storage. And energy, this is coming with energy recovery too. So this is one thing. Another thing is that a whole energy recovery system has to be associated with any place when you have solar power production and solar thermal production. So when you have those processes, they have to automatically come with some kind of thermal storage. Otherwise, you will be wasting a lot of energy. And of course, I didn't say anything today about energy efficiency, but energy efficiency is just something which should be on the background. It is mandatory condition. You have to start whole design. The thermal storage probably should be the second step after saying to yourself, okay, I did everything from energy efficiency perspective to achieve. Otherwise, if you will be dealing with very ineffective system, it will be much more difficult to take care of those effects.
It's very difficult. It has to be passive, active, has to be a lot of things going into play. Well, the second question has to do with the PCMs, and you've shown a lot of plots and very, very, very nice plots on the effectability and the effect of the PCMs, and we talked about this yesterday also. We see in the plots that you've shown that, for example, when we're going up in the charging process, we don't really see that, that inflection that you see, okay, PCM's there. But you can see it on the discharging. It's noticeable in the results that you've shown.
Well, actually, you can see this on the testing.
This was not the one. Actually, it's another one, but I don't remember now.
You can see this here too.
Mm-hmm. Well, you can see.
I did a lot of dynamic testing on PCMs, the hotbox testing, and you can see this on dynamic hotbox testing. You can see little bit. This is like saddle here in this area, when actually material is starting to charge and discharge. So you can see this. You have to, if we have more time, maybe at some on the private conversation, I can show you a couple of slides from the hotbox testings, when actually you could see this. So you can see that PCM work, and actually you can tell exactly going for the temperature range. You have something like 28 degrees PCM or 29 degrees PCM.
And another thing is, still looking at this result, is what Antonio was talking about. So if I had to apply PCMs, for example, in a retrofit or a new design building, We have an idea basically where we should position it. It's more or less clear. But since you talked about, and very important, the fast and the slow processes that are involved. For example, we've done things in the past that did not work very well out. For example, a PCM shutter, where you know that if you put in a PCM that you have a temperature peak of 35 degrees, it will just like, just click your fingers and it's done, it's over, and you have nothing else to work with. How do we couple, since we're talking with these single peak temperature, PCMs, and how do we work this out? So if we're talking about long processes in terms of building amplitude or oscillation temperatures, how do we work out with the thermal inertia so you make the PCM more effective? Because we see these applications that sometimes they come into play, they do their job, and basically it's very instantaneous, if you like. It's like,
yeah, that's a very good example. If you put PCM just under the roof surface, there'll be like 5 minutes, PCM will be charged and no PCM anymore.
That's over.
Yeah. Yeah. So actually this is an example with the roof application here. This is a metal roof on top of that. Between metal roof and there's and just PCM system, you have air cavity, you have reflective insulation, you have fiberglass, and then you have PCM. So actually your thermal load from the roof is going down. It's still, you have harmonic thing, but there's enough low to make sure PCM takes care. Depends on how much PCM you have to get to that design that PCM will be working in the way that it will be capable to absorb enough energy. So that's, it has to be compatible with energy storage density for the PCM. And here, this is nothing, I haven't done anything extra insulation. I just moved the insulation in the right place and moved PCM to the right place.
And so like as a rule of thumb, could I say, for example, if I had to think about building components, I would say, okay, if I had to put PCMs on floors, I would put them on the most inner surface. Have to put PCMs on walls, maybe on the most inner surface. And in the case of roofs, maybe not on the inner surface, but somewhere in between. But this will...
Actually, well, you have to ask yourself question if you can afford putting PCM in all walls, roof, and floor. So that's number one thing. People are not doing anymore, just architects, actually mostly European architects, they try to put PCM, they called it PCM house, and this was mostly for marketing purposes. And they finish all walls with PCM, which actually not necessarily all those walls needed that PCM. So the big thing is to understand the design and see, okay, where will be my place, my PCM will work the best way, most economically justifiable way. Mm-hmm. So this is not like we put PCM. We need to ask yourself, what is the reason we need PCM for? And if we want to shift the loads, we have to find a way to shift these loads most effective way. Either we can find it will shift when we will put that PCM in the floor, or it will shift if we'll put that PCM in the ceiling or somewhere else. So this is the first question, what we will do. Not just, we are just, it's like children in a sandbag. Let's do, this is my toys, and I'm making everything around with my toys. And this is not, we are just much more mature people, we are engineers, so we have to learn how to design the system the way, like, if you go to dentist and you have one sick tooth, dentist will not pull all of them, yes? So that would be, yes.
I would like to make one simple question. First of all, thank you very much for the knowledge share. I would like to ask you, as we all agree, inorganic PCMs have broad advantages over organic PCMs. However, I could identify two major drawbacks, which is corrosion and phase separation a long time. My question is, how can we cope with those disadvantages when we want to use inorganic PCMs in a lost or kind of lost constructive application? What I mean is, if I would like to apply inorganic PCM in a floor system, for example, how would I could overcome those challenges over time?
I'm not saying that there are solutions for everything what you said, but I think that the major solution is make PCM suppliers honest. So in Europe, you guys develop wonderful standards for PCM performance, for PCM testing, and there's a whole association working on this. But I'm not sure if there's a good transmission, those standards into the products which are offered by industry. So that's one thing. Those products have to be durable, and there are some PCMs for different applications. We may use PCMs which have to go in the whole lifespan, couple hundred cycles. For other applications, you will have PCM systems which will have to go to 1,000 cycles, tens of thousands of cycles. And that system has to be tested for that amount. I'm not sure if all industrial partners or suppliers are that rigoristic in supplying. So that first thing, before you decide to move on with the material specification for the construction, you have to talk with the manufacturer. You have to talk with good chemical lab, and you have to test the material. And I think that it shouldn't be that way. If you buy TV, you have warranty that that TV will work for 6 years or so, number of years out there of hours. The same should be with PCM. So that's the one thing, and actually I think that there is a very large number of manufacturers who are suffering because of some other dishonest manufacturers. And I think that industry associations should actually be very specific on this. Who can put product on the market with specific parameters? In US, there is a so-called Federal Trade Commission, FTC. And FTC is responsible for checking how industry is following labeling of the materials. And it is very restrictive. I work with them several times, and this is just very easy. If you don't follow this, sometimes even $200,000 fee company has to pay.
I'm not a specialist in the field, but I am curious about it mainly. And I have a few comments considering the importance of energy consumption in houses in the US that you presented. I wonder if that importance of energy consumption in houses is not mainly related with cooling needs in general, globally, instead of heating needs. At least here in our conditions, we have, I think, important cooling energy needs for buildings. And in fact, our traditional construction in Portugal, stone construction with very wide walls, were conceived for keeping the inside temperature always quite cool, and people would use mainly wood for heating when needed. But the building itself was conceived for keeping a fresh indoor space. For those conditions that I'm referring, the cooling needs of houses, do PCMs offer some benefit or not so much?
Actually, I think that a lot of PCM applications have been developed for countries and for locations with very significant cooling loads. So actually they have been dedicated to cooling loads, not to heating loads. And actually, I was one of the proponents of using seriously PCM for heating applications for many reasons, but PCMs have been historically, that in the last 2-3 decades, have been used from the perspective of reduction of cooling generation, cooling type loads, thermal loads. So they can offer very significant load reduction. Of course, it's difficult to say about those reduction in country like Portugal. You have very specific climate, and you have, I would say, very specific type of loads where, in my opinion, you can actually use a lot of which has been developed during 1970s and 80s, which has been called passive solar architecture, which can provide free heating and free cooling for those buildings. And I think that significant part of the Portuguese houses can be zero energy without going into the extremes with going with thermal insulation and some other stuff. So that's good. You're in very good situation, but I think that in your case, big cities, commercial buildings, office buildings, those facilities which require much more precise hospitals, schools, space conditioning, they may significantly benefit. So that will be my answer.
Sorry. Well, first of all, thank you very much for this brilliant presentation on PCMs. We have been talking for the past few days, and we have learned so much about PCMs, and especially PCMs and applications in buildings, that I cannot tell you how much and how grateful we are for your presence here and over the past few days. And especially this presentation, which was most enlightening. And I only have like 2 simple questions. One of them is concerning, again, the flying duck. And I was wondering, just looking at the picture, why do you observe such wide changes in an 8-year period, specifically in California? What happened during those 8 years in California that justify this kind of change? That was one of the questions.
Solar power were added. So every year they were building new solar power. So that extra solar, that was negative energy going to the grid. So that value was just taking power from the grid, what you needed, and it was a situation that actually they had to start thinking about shutting down power plants. So and actually California is a good example to see what is the first reaction of a lot of governments. Their first reaction was build so-called battery banks. So they build a huge facility of the lithium batteries, which actually take over that extra produced solar power. So that's and can you imagine tons of lithium going into environment? So that's the. I'm really scared about what's going on with this. Considering that we have some other sources, we can do this in different way. I'm not saying that this has to be eliminated, but there are some other sources with lower environmental impact.
Yes, I think so. One of the one of the parameters that lately I've been trying, at least to talk about to students, is this energy return on investment, EROI, which is a nice, say, ecological parameter. And people who are experts in doing this job, because they do a life cycle concerning energy, often realize that some of these technologies are really not worthwhile, because the EROI, either for producing energy or the other parameter for accumulating energy, is not really worthwhile. You're investing or putting in a lot more energy than you're getting from these devices, and this is a sort of consequence. And this is related to my second question, which is a very broad question. I guess it's probably very difficult to answer. Is how do you force? Well, if someone wasn't really an expert, we are not. I guess we are just learning from you right now. But if someone wasn't really an expert, perhaps the first question that this person would probably ask himself or herself is, isn't this whole thing a bit too complicated? Especially when you mentioned that the mechanical engineers sometimes tend to overcomplicate systems and make them introduce in mechanical, in the electrical devices or technologies that make things truly complicated. So, and when you say that you have like 2 PhD students, chemical engineers working, 24/7, just to develop that formula, that ideal formula, which has to be fine-tuned for a given application or for a given building, and then that building for the, the ceiling or the floor or a given wall, isn't, just saying. I mean, don't see it as a criticism, but isn't this, a little bit complicated? Shouldn't it make you feel a little bit, how can I say, of fearing of the technology?
I hear what you say, and actually that's the reason why we work. If you remember one of my slides, I showed that we work on a number of the PCMs from the whole range. And it is the reason why Department of Energy funded project for us. When we offer that we will not develop a single PCM, we'll develop just a family of PCMs on different. So actually the whole idea is just put a number of PCMs with open source that industry will be able to use those PCMs between 5 and 65 degrees. And then this way of designers. Designers need to know exactly what to, even talking about cars or bicycle, just you will not talking about bicycle. You will not put one type of derailleurs into the bicycle with SRAM, or just you can put SRAM derailleurs from different company, and you will have shifters with different pull size, so you will be not able to run those derailleurs. The same with PCMs. Just you have to remember that simply there are applications which require different temperatures. That knowledge is a basic knowledge and supposed to be basic knowledge for architects. So that's, this is not like science fiction. This is just like couple temperatures. Just that stuff has to be, you need to design, build real commercial, high-end, very expensive commercial buildings. So this is just task for, just modeling. But for just simple buildings, this is just taking just like from the shelf. I'm taking PCM because this temperature should be like this in this climate.
Thank you very much again.
Mm-hmm.
And, we'll just, I think we can stop here.
Thank you very much. Thank you for coming. Great pleasure.